Previously, we looked at examples of exponential growth. Now we're going to be looking at examples of exponential decay. So we will be working with functions that are decreasing rather than increasing, and so the derivatives are going to be negative. In this example, xenon 133 has a decay rate of 14% per day. The rate of change of an amount N of this radioactive isotope is given by the derivative equal to a negative 0.14 times N, where N is the function. We want to find the function that satisfies the equation, and we're going to let N sub 0 represent the amount present at time t equals 0. So N sub 0 is our initial amount. Now in our notes, the general equation that we use to represent exponential decay is given by P sub t equal to P sub 0 e to the negative k times t, where P sub 0 is the initial amount and k is our decay rate. Here in this specific example, we're using N instead of P. Now our decay rate, k, is given by 0.14. The negative is in the formula itself. And then our N sub 0 is our initial amount. So our function then is going to look like N sub t equal to N sub 0 e to the negative 0.14 t. For part B, we're going to suppose that 1,000 grams of xenon 133 is present in time t equals 0. How much will remain after 10 days? So now we're assuming that our N sub 0, our initial amount, is equal to 1,000. So we're going to plug that into our function here. So N sub t then is going to look like, now that we have a specific initial amount, we can put that into our function here. 1,000 e to the negative 0.14 t. Now if we want to know how much will remain after 10 days, we're going to evaluate t equal to 10. So we're plugging 10 in for t. So we're going to have 1,000 times e to the negative 0.14 times 10. And when we evaluate that in the calculator and then approximate it, and here I'm going to approximate it to the nearest gram, we're going to have 247 grams. And that's how much will remain after 10 days. For part C, we want to know after how long will half of 1,000 grams remain. Well, what this is asking for is the half-life. And if you've looked at the notes, you already know what the formula is for calculating half-life. But let's suppose for a moment that you haven't looked at the notes and you don't know the relationship between the decay rate and the half-life. So here we are starting out with 1,000 grams, and we want to know at what time t will we have remaining 500, since 500 is half of 1,000. So what we're trying to do here is we're trying to solve for t. We want to know for what t value do we get just 500 grams left. So we're solving for t. So we're going to divide both sides by 1,000. And then after dividing both sides by 1,000, notice that 500 over 1,000 reduces to 1/2. So we have 1/2 equal to e to the negative 0.14 t. Now to solve for t, we need to take the natural log of both sides. And then when we take the natural log of both sides, the property of logarithms allows us to bring the exponent out in front of the logarithm. So this is going to then look like we're going to have the natural log of 1/2 equal to a negative 0.14 t times natural log of e. Alright, and then we know that natural log of e, that is just equal to 1. So now to solve for t, we can divide both sides by a negative 0.14. So we're then going to have t equal to natural log of 1/2 divided by a negative 0.14. Now at this point, if you wanted, you could go ahead and plug that in the calculator and get a decimal approximation for t. But just for a second here, I want to simplify what we have here. We have And there's a reason why. I'll get to that in a second. So we have natural log of 1/2. Well, the property of logarithms says that I can take that quotient and break it up into subtraction. So I can write it as natural log of 1 minus natural log of 2. And that's one of the properties of logarithms that we reviewed previously. And then this is being divided by a negative 0.14. Now the reason I did this, well, one of the things is the natural log of 1, and that's just equal to 0. Natural log of 1 is. So that's going to go away. So then what we have here is that t is equal to a negative natural log of 2 divided by a negative 0.14. Well, the negatives cancel, and we have that t is equal to natural log of 2 divided by 0.14. Alright, so now the reason I went through simplifying what t is equal to is because if we take a look at what we have here, this is natural log of 2 divided by 0.14. 0.14 is our k value. And if you look in your notes, you should recognize that this is natural log of 2 divided by k. This is the formula that is in your notes for calculating half-life. You simply take natural log of 2 and then divide it by whatever k is, and that'll give you the half-life. So once you have this formula, you don't have to do all of this work that we just did here. Okay, you can simply use this formula. But I kind of wanted to show you why the formula is what it is. Alright, so then if we plug this into our calculator, natural log of 2 divided by 0.14 is approximately 5. It's 4.95, which I'm going to approximate to the nearest day. So approximately 5 days is how long it'll take the 1,000 grams to be reduced to half. In this next example, of an initial amount of 1,000 grams of plutonium-218, how much will remain after 20 minutes? Plutonium-218 decays at a rate of 23.1% per minute. Well, we know that our model for exponential decay looks like this equation here. We have P of t equal to P sub 0 e to the negative k times t, where P sub 0 is the initial amount and our k is our decay rate. Notice we have a negative sign here because we are experiencing exponential decay rather than exponential growth. Here we are told that the initial amount is 1,000 grams, so that is what P sub 0 would be. P sub 0 is equal to 1,000. And then our decay rate, if we write that as a decimal, k then is going to equal to a 0.231. So then our function is going to look like P sub t equal to 1,000 e to the negative 0.231 times t. Now we want to know how much will remain after 20 minutes. So when t is equal to 20, we want to know the amount that remains. So we're going to plug 20 into our function here. So we have 1,000 e to the negative 0.231 times 20. Now when we plug that in our calculator and approximate it, we get approximately 9.85. And here I've rounded it to 2 decimal places. So 9.85 grams is how much will remain after 20 minutes.